The neutrino, although it is ubiquitous, is one of the most elusive particles in all of nature. Because the neutrino has no mass, it has no charge and moves at extremely high speeds, its mean free path before collision can be several thousand light years in even very dense matter like lead. And yet physicists, Dr. Cowan and Dr. Reines, had devised a clever experiment to pin down this neutrino. Dr. Clyde Cowan from the physics department at the Catholic University of America is going to describe his discovery of the neutrino. Dr. Cowan.
How do you do? Well, the discovery of the neutrino was merely one event in a long series of events that began really with the discovery of radioactivity by Becquerel in 1896. As you know, radioactivity was soon found to display three different aspects. One was the emission of alpha particles, helium nuclei. Another kind of radioactivity was the emission of gamma rays. And a third kind was the emission of electrons, fast electrons called beta rays, or beta particles. As physicists explored these new phenomena and worked with them, a strange puzzle arose in the matter of radioactivity. This puzzle involved the conservation laws of energy and of momentum. As you know, the law of conservation of energy and the law of conservation of momentum are two of our most fundamental laws of nature and had been for a long time before the discovery of radioactivity. And it was found that while two of these types of radioactivity, alpha decay and gamma decay, obeyed the laws of conservation of energy and momentum, apparently the type of radioactivity called beta decay did not. Apparently did not. It goes something like this. In any system in nature, one can describe a total energy, which if I say plot energy vertically could be represented by that line. And then if that system undergoes a change to a lower state of energy, say here, then it has lost, that system has lost a certain amount of energy given by the difference between these two levels. Always, in every instance before the discovery of beta activity, this missing energy could be found in some other system. It had gone from this system to some other system which had been connected with this system. For instance, if this was the energy of a nucleus which was about to emit an alpha particle, then this was the energy of that nucleus after it had emitted the alpha particle. Then the difference in energy was just that energy contained by the alpha particle and by the recoiling nucleus. And so if one had a particular kind of alpha particle decay and plotted energy in this direction, and the number of alpha particles in this direction, then all the alpha particles that came from this decay would be found to lie in one particular very sharp line. Not exactly sharp because there are problems of recoiling nuclei, but essentially a very sharp line of energy. So this would be the spectrum, the energy spectrum of the alpha particles. And with gamma decay, the same thing was found. If this was a nucleus, excited nucleus, about to emit a gamma ray, and this is the nucleus after the emission of the gamma ray, then the difference in energy would be found in the total gamma ray energy that was emitted. Let's suppose that, just for the sake of using some numbers, suppose that this energy level is 1 MeV as compared to this energy level, a half MeV. Then 1/2 MeV would be found in the alpha particle or the beta particle, or the gamma ray. With beta particles, however, this energy was never found. If we're talking about beta decay, this is the nucleus about to emit a beta ray, and this is the nucleus after the emission of the beta ray, then 1/2 MeV should be contained by the beta ray and the recoiling nucleus. And as the beta ray, an electron, is very light compared to the weight of the nucleus, it would contain almost all of the energy and momentum and should contain a 1/2 MeV and should lie here. On the other hand, none ever lay there. Sometimes it would be here, sometimes here, sometimes here, 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 here. And if one took not just a few beta decays, but measured the energy for each beta decay for many beta decays and added them all up, one would get a spectrum which would look something like this. It would go out and approach that endpoint, but would never quite reach it. Apparently, energy was being lost by this system. Now, let's look at the beta decay in more detail. We can represent a beta decay as the decay of a neutron, for instance, that is contained in a nucleus, where the neutron changes into a proton. Suppose this is some nucleus, and this is a given neutron in that nucleus. And because of the number of neutrons and protons in the nucleus, that neutron changes into a proton. The nucleus would rather have a proton rather than a neutron. And so that neutron decays and becomes another nucleus, another element, in which that neutron now is a proton. And in doing so, that neutron emits a beta ray, an electron. It produces the electron, it creates the electron at the time of decay. And we can write that equation then in the normal way. A neutron with no electric charge yields a proton with positive electric charge and a negative electron. Notice the total amount of electric charge is conserved. There's no charge here, and the sum of the positive and negative charges here sum to 0. Another type of beta decay which was known was the inverse of this, where the proton converts itself into a neutron and produces a positive electron. For instance, a positive proton becomes a neutral neutron plus a positive electron, and again charge is conserved. But the energy of these electrons, the total energy of these electrons, which should lie in this line, was found to be always less than the proper amount. Now, this caused great concern among physicists. People used their most sensitive equipment to try to find where this energy was going to, and failed. Not only was energy was missing from this, but also momentum was missing. If one started out with this neutron at rest, this nucleus at rest, then one had an electron shooting off with some momentum in one direction, and the nucleus recoiling a little bit in the other direction. And as the momentum was 0 before the event, it should be 0 following the event. And these two momenta should add up in the style of vectors and should be 0, because it was 0 to begin with. This was found not to be so. There was always some additional momentum in the system. Even angular momentum was not conserved. I won't go into the details at this point, but one could measure the angular momentum. Knowing the angular momentum of the initial particle, we know the angular momentum of the final particle. Well, for instance, suppose this is a free neutron, not in a nucleus, but a free neutron. Then it's very simple. The angular momentum is given by its spin, and we say that it has spin 1/2, and so the neutron has spin 1/2, which, say, is upwards, plus 1/2. Now we know that the proton has spin 1/2. So it has either spin up or spin down of 1/2. Also, the electron has spin 1/2, spin up and spin down 1/2. These are measures of the angular momenta of these particles. There's no way to add these, one of these and one of these, to get this 1/2, you see. You either have 0 if you choose them in opposite directions, or you have 1, never 1/2. So even angular momentum was not conserved. Well, there was great concern among physicists about this problem, and some prominent physicists began to take the view that while energy and momenta are conserved in nature in the large, when one gets to this very tiny region of space, the nucleus, perhaps it's not conserved. Perhaps energy and momenta are actually being lost from the universe. This is a violent thing to assume because it chops away at the very basis of our modern physics. Other physicists reserved judgment and continued to wonder about the problem, and one of those physicists whose name will live forever with this subject is that of Wolfgang Pauli. Pauli in the years between 1920 and 1930 considered this problem more and more and came to the hypothesis that there is another particle emitted along with the beta particle which is escaping detection, which has spin 1/2. If you add 3 of these 1/2 vectors together, putting the 2 of them up and 1 down, or 2 down and 1 up, you can get 1/2, a total of 1/2. This other particle would take up the missing energy. If the beta particle had this much energy, then this missing particle would have that much energy, and the sum would add together, and one would not have any loss of energy. Well, Pauli was embarrassed to propose this. He proposed it in very mild ways, in talks to his colleagues and to small scientific groups, and almost invariably he was laughed down for inventing an excuse to get out of having to cope with the loss of energy and momentum. People just didn't take him seriously, although he was, at that time, certainly a well-known physicist. That is, most people did this except for one, and that one was Enrico Fermi. Fermi had been working with the theory of radioactivity in gamma decay, and also the production of photons, not only from the nucleus, but the production of photons from atoms which were excited, and developing mathematical expressions to predict these events. And he took Pauli's suggestion seriously, and he said, suppose there is a particle. What is it like? And what can I say about it? Well, he assumed that there was a particle. Obviously, electric charge is already conserved here, so the additional particle could not carry electric charge. It had to be neutral. Secondly, it had escaped all detection by the most sensitive instruments of the day, and so it must be very small and very penetrating. Pauli had proposed the word neutron for this particle, but the word neutron had already been taken for the other particle, the nucleus, the nucleon neutron. So Fermi, being Italian, took the word neutral and changed it, put the diminutive of the Italian ino on it, which means little, made the word neutrino, gave it the symbol nu, and so we had the first look at the equation that Pauli would write and Fermi would write. They would add that particle and call it the neutrino. It had zero charge. It was very penetrating. In order to make the theory, the mathematical theory, fit the facts, and the facts were the given shape of beta decay spectra, the given half-lives of beta decaying nuclei, knowing the energy levels that the nucleus would transit between, the theory could predict these if the proper properties were given to the neutrino. These properties turned out to be very surprising. Not only would the neutrino be small, but it would have extremely small interaction with matter, and it would travel with the velocity of light. It would have no mass. Its mass would be zero. And so this was a particle which sort of challenged us all, challenged physicists of that day and this day to try to detect. The neutrino lived in theory. It succeeded, the theory succeeded beautifully in predicting half-lives and in energy spectra and so forth of beta decay in the nucleus. So the field of physics was divided. Many physicists felt we had the answer because of its success in predicting the facts of beta decay. The neutrino had to exist. Other physicists felt that this was circular reasoning. You had something, a situation, you postulated an answer which would correct it, and then you put it back in and find that it does correct it, and the correction justifies the postulation. Well, this can be a type of circular reasoning which many people didn't like, and so some people continued to feel that the neutrino was merely an excuse for the facts, and that it really was not a true particle. As time went on, not only nuclei were found to decay by beta decay, but also other things such as mu mesons, pi mesons, and other particles that were being discovered. Well, a number of people, as time went on, a number of people used newer and more modern techniques to try to observe the neutrino freely. The idea was, if the neutrino is stealing energy from this system, the only way you can prove that a theft has occurred is to find the loot in the pocket of the thief. Just having the loot disappear does not prove that there's a theft and that there is a thief. So physicists would like to then find the thief, find the energy in his pocket while he's running away from the site of the theft, after the event. Well, a number of attempts were made with increasing precision, and these attempts failed to observe the neutrino directly. Let me indicate one way in which the neutrino could be caught with this energy. If we look at this equation, neutron plus proton, giving a negative electron and a neutrino, we can play with that in the sense of an algebraic equation, providing we stick to certain rules. Each of these particles has an antiparticle. There is an antineutron, an antiproton, an antielectron, and there must, in that case, also be an antineutrino. So let me draw that up there. So that's an antineutrino for conservation laws which we have more modern. One can change these from one side of the equation to the other if one changes particle for antiparticle, or vice versa. For instance, I can take this top equation and bring this neutrino. No, let me do it the other way around. let me bring this electron over to the other side of the arrow and write it an electron plus a neutron yields a proton plus an antineutrino. Now I must make that electron into the anti-electron, and I do that merely by making its sign positive. That reaction is the same as this reaction, physically. Furthermore, in the realm of these very small regions, elementary particle interactions, what goes forward can come backward. And so I can write this the other way around without changing anything. I can merely reverse the arrow, and then it doesn't make any difference. I can write it this way. The antineutrino plus the proton, where I've taken that side, gives a neutron plus a positron. That, again, is the same reaction. But notice, suppose we have this neutron emitting this antineutrino, and then at some distance away we put another proton. We put a proton there as a target. And let this neutrino be that neutrino, and that neutrino strike that proton, then this reaction can occur. The proton can be converted back to a neutron with the production of a positron. This is called inverse beta decay, but it's really the same reaction. Now you've heard of and you've learned of the concept of cross-section, which gives the probability for this to happen. And this cross-section is given commonly in terms of square centimeters. And we can quote the cross-sections for this to happen. Given the neutrino a certain amount of energy, say a few MeV, the proton at rest, it was found that people could get down to small cross-sections of the order of 10 to the minus 30 square centimeters. This is very small. Then on the basis of neutrinos, which were presumably coming through space and from radioactivity in the Earth, penetrating the Earth, it was calculated that this might be, a limit might be set of 10 to the minus 33. But this is far from being the cross-section that Fermi's theory predicted. Fermi's theory predicted that this cross-section, for this to happen, if this is, say, a 2 or 3 MeV neutrino, would be not 10 to the minus 33, but about 10 to the minus 43 square centimeters. This is perhaps the smallest number up until recent years, when this number, other neutrino cross-sections of even lower value for other events have been thought of. This was the lowest, smallest number ever conceived by man as a serious model for reality. A very small thing. This meant that the neutrino could penetrate very well. Let me give an example of how this might work from our own experience. When Dr. Reines and I, working at Los Alamos, were wondering, along with many people, about this problem of the neutrino, we said the sun should be emitting neutrinos. Many people said that. And these neutrinos should be coming to the Earth. And based on the theory and the known capacity of the sun to produce energy, it was found that about 10 to the 12th neutrinos, 1,000 billion neutrinos, should be passing through every square centimeter at the Earth, of the Earth's surface, per second from the sun alone. That's a lot of neutrinos. 10 to the 12th per second per square centimeter. And we said, well, suppose we succeed somehow in detecting neutrinos that come from the sun, how would we prove that they're coming from the sun? Suppose we can't tell what direction our detector is going to be pretty fancy just to detect the neutrino, much less tell what direction it came from. Well, the answer was obvious. You run the detector at noontime, and you get a certain counting rate. And then you wait till midnight when the sun is on the other side of the Earth, and you make another measurement, and the Earth has absorbed some of the neutrinos, and you know they came from the sun. Well, we calculated using this cross-section and the energy of the neutrinos presumably coming from the sun, and we found that the difference was so small it could never, ever be detected. The Earth would absorb so few neutrinos that it would be undetectable in a practical sense. Well, we said, let's do this experiment at a time of an eclipse when the moon helps us. It's between the Earth and the sun, and we'll do this experiment. And the same answer. The moon didn't help. We said, well, suppose we could find some angel that could talk to the Lord and say, stack up moons, please, between here and the sun. That ought to absorb them. And the answer was no. There'd be such a little difference in counting rate that you couldn't detect the difference. Well, we said, goodness, suppose we had even more authority and we said stack up moons for a long distance. How many moons stacked end on end would it take to produce a detectable difference? And the answer was the moons would have to be stacked up across the entire universe, not the galaxy. Too little. The entire universe. Then there would be a detectable difference in the neutrino signal. That's how small that cross-section is. Based on that kind of thought, some physicists and some well-known physicists said this problem of the neutrino will remain forever a theoretical one. No one will ever be able to detect the neutrino in the free state because it'll penetrate his equipment so readily it won't interact with his equipment. They, however, made the error made by so many of us of not seeing well enough into the future and seeing the developments that would occur in the future. One of these developments was the development of atomic energy, the discovery of fission and the production of fission on large scales, such as in exploding fission bombs and in fission reactors. Now, when uranium fissions, it produces fission fragments. These fission fragments, being nuclei, are rich in neutrons. All of them, or most of them, are rich in neutrons. So they undergo beta decay by this reaction that I've written, and they emit antineutrinos. And it had been realized that this type of beta decay occurs in the fireball of an exploding atomic bomb, or an atomic bomb that has just exploded. The fission fragments in the fireball emit these neutrinos as they undergo beta decay. And when you calculated the number of neutrinos being emitted by a fireball from, say, a 20 kiloton bomb, which is sort of a nominal size, 20,000 ton TNT yield explosion, you found that there were quite a few neutrinos coming through every square centimeter per second at a distance of a few hundred feet from the bomb, from the fireball. There were of the order of 10 to the 17th neutrinos, antineutrinos per square centimeter per second, or perhaps 10 to the 18th total. The fireball, of course, rises very fast, and so if you had a detector a few hundred feet from this atomic bomb, you would see there would be a few, say 10 to the 18th neutrinos pass through that detector. That's considerably more than the sun, isn't it? Sun being 10 to the 12th. Also, these neutrinos are a bit higher in energy, so a bit higher in cross-section for this interaction. So if one put enough protons in front of these neutrinos, then some of these protons should capture neutrinos. Here, another factor comes to mind, comes to help us, and that factor is attached to the name Avogadro. As you know, the Avogadro number gives the number of molecules of any substance in one molecular weight of that substance. For instance, 18 grams of water contains 6 times 10 to to the 23rd, about that. A tablespoonful of water, 18 grams of water, contains about that many molecules. That's a very large number of molecules. And each molecule contains 2 protons as hydrogen, H2O. And so the total number of protons contained in that tablespoonful of water, 18 grams of water, is about 10 to the 24th protons. Now, no one can visualize how big that number is. You just can't contain that number, just as you can't visualize really how small that number is. But let me give you an example. I once saw an advertisement for a kind of grass seed that claimed that there were 1 million seeds per pound in the grass seed. And I wondered about this. I happened to have some of that seed, and I made a count, and I found that that was wrong. It was only about 650,000. But if we assume the million figure, say there are 1 million seeds in a pound of grass seed. Suppose one had that many grass seed, then he'd have how many pounds? He'd have about 10 to the 18 pounds of seed if he had that many seeds. How much is that? Suppose one let that amount of grass seed flow over Niagara Falls instead of water. And at the same rate, ton for ton, a ton of water, no, a ton of grass seed, over both sides of Niagara Falls, Canadian and American, per second, how long would it take that many pounds of seed to flow over the falls? Well, if you look up the average rate of flow of Niagara Falls and calculate this, calculate the time it would take. You might guess now how long that would be. Would that be a day or a week? A lot of water flows over Niagara Falls in a week. Now, the answer is something like 3,000 years. 3,000 years for that much seed to flow over Niagara Falls ton for ton. So that's a big number. And that big number, when combined with this big number, is even bigger. You see, 10 to the 24, and I add 17 to that, so I've got 10 to the 34. I have 10 to the 41, huh? And that's a measure of the rate. If this is the cross-section, or this is the flux, and this is the number of protons, then if I multiply that by that 10 to the minus 43, I'm not so bad off. This only gives me, what, 10 to the minus 2. If I make an error in my arithmetic, please correct me. This 10 to the minus 2 is not such a bad number. That's per second. That's the number of interactions that would occur per second. So we figured, let us use the neutrinos that come from an atomic bomb. Let us put enough water, so we have a lot of protons there, so that we get a lot of counts. We get this many counts out of each tablespoonful of water. Let's put a ton of water there, roughly a cubic meter of water, near an atomic bomb, and see how many interactions occur. Well, we planned this. Fred Reines and I were working at that time with our groups at Los Alamos in the testing of nuclear explosions in Nevada and out at Inuiatok. And there were a number of such nuclear explosions scheduled, and we got permission to go ahead with this kind of an experiment. Enrico Fermi was working at Los Alamos at that time. This is very early 1950s. And he said, yes, the experiment ought to work. And the laboratory said, yes, it ought to work. We should be able to see these neutrinos if they exist using the neutrinos coming from atomic bombs. Go ahead and design this experiment. Well, this is the experiment we designed. It's not the experiment we did, thank goodness, as you'll see. When we contemplated using this 20-kiloton bomb, we contemplated doing this in Nevada, and these explosions were commonly set off on the tops of towers, which was perhaps 100 feet or a little higher than that. And then there was a cab up here on the tower, and the nuclear explosive was put up there. And then at time 0, button was pressed, this thing went off, and a fireball was made, which didn't quite touch, almost touched the ground. Didn't quite touch the ground. 20 kilotons of TNT explosive equivalent. This fireball would pause there for a fraction of a second. The blast wave would hit the ground, come back, hit the fireball, and the fireball would bounce into the sky at a high rate. So one had the time while the fireball was sitting here, plus a very short time as it was rising, before it got too far away, 100 to 200 feet away, for us to see this. Now, an atomic bomb explosion does a number of things. It not only puts out neutrinos, antineutrinos really, but it generates heat in the form of photons. Let me indicate that by gamma heat radiation, which is extremely intense. It melts the tower and vaporizes the tower. The tower is gone. A blast wave of extreme intensity, which can break up anything known to man at that distance. And so we had to put a detector within a couple of 100 feet and then go back to that detector after the explosion and find out if neutrinos had interacted with these protons in the water. Well, we thought what we should do is come out here a little distance and dig a very deep hole. And then down partway in that hole, put a ceiling and backfill the hole with dirt. Now the energy, the gamma rays coming from this thing, the radiant energy, would be absorbed by the ground and would not penetrate down into this chamber. Furthermore, the blast wave would come running through the ground and would shake the dickens out of this chamber. And so we had to protect anything we put in here. So we thought we would put a vacuum vessel in here, a big steel can, and evacuate that, make it very low pressure, and then hang our detector from the top. A ton or two of water with its electronics and equipment to detect this interaction should it occur. Now at time 0, when this explosion went off, we'd cut the rope holding the detector. The detector would now fall, and it's falling in a vacuum. The shock wave would run through the ground. The heat would be held back. Neutrons also would be absorbed by the ground. Just the shock wave would run through here and would shake the teeth out of that tin can, that steel can, but the detector falling in a vacuum wouldn't know it. After the shock wave had run through, this hole being deep enough, there was down here some springs and some foam rubber and feathers and pillows, and the detector would land there and wait for us to come and dig it out and see if it had actually counted. The last thing to decide was how far out from the ground zero should this be. Well, it didn't make, turns out, a lot of difference whether it was 100 feet or 150 feet. It didn't really make much difference. So for luck, we picked the number 137 feet. If you think physicists are not superstitious, ask your instructor what that number is, or really what the reciprocal 1 over 137 is, and why. And you'll see that physicists are superstitious. Just for luck, we picked 137 feet. And we were drilling in this ground in Nevada in order to begin this design of this experiment when the physics group division to which we belong at Los Alamos, I keep saying we, I should put down my colleague's name, Frederick Reines, R-E-I-N-E-S, who was also working on these with me in these thoughts. We gave a talk to a seminar at Los Alamos, the physics division, and outlined this experiment. And it was obviously such a harebrained experiment that it was going to be very difficult, very expensive, and could probably fail just because of our own stupidity. And we'd have to do it over and over again, no matter what the result. Nevertheless, we had the go-ahead to do it and had a group working on it. At the end of the lecture, Dr. Kellogg, the head of the division, said, "Please think once more. Fission occurs in nuclear reactors, and neutrinos are produced from nuclear reactors just as well as from nuclear bombs. Can't you possibly sit near a fission reactor and use those neutrinos quietly and for a long period of time?" Well, the number of neutrinos that were coming from fission reactors, as close as one could get to the fission reactor, right up against this wall, was not 10 to the 18 or so, but more like 10 to the 14 per square centimeter per second. And that was a factor of 10 to the 4 in intensity, and we calculated as best we could expected backgrounds, and we had come to the conclusion that that was just not enough. One couldn't get enough signals from neutrinos to overcome backgrounds from radioactivity and cosmic rays. What signals were we expecting? Well, suppose this occurs in the water. A neutrino comes along, converts a proton into a neutron and a positron. We knew that the positron would soon, very quickly, capture with a negative electron, E plus plus E minus, and give 2 gamma rays. And the neutron would float around and after some while would capture in hydrogen with a proton to yield deuterium plus a gamma ray. And these gamma rays we could detect by means of crystals or Geiger counters or something. And so we'd get pulses from these gamma rays. And we figured we'd get a couple of hundred pulses from this atomic bomb while it was sitting there at the ground. In response to Dr. Kellogg's request, however, we got together again that evening and said, let's go over all the numbers again and see if there isn't some possibility of doing this. And then lightning struck. We realized something that we had been passing over. The fact that the pulses from the positron and the pulses from the neutron occur in pairs, always related to one another. One never has the positron and then the neutron separated independently. One always has the positron followed by the neutron a few microseconds or tens of microseconds later. And if we looked not for single pulses and added up the single pulses, but looked for what are called delayed coincidences, where these pulses occur in causal relationship, that should give us a tremendous factor against background in favor of the signal. In fact, a factor of about 1,000,000, 10 to the 6th. And that overcomes this factor of 10 to the 4 here, and we could, in fact, thank goodness, use a reactor to do this experiment. Well, to make this long story shorter, we called next morning, told Kellogg that we were calling off this experiment. We got our groups together, canceled all of our plans, and began a new set of work aimed at using a reactor. Now, in using a reactor to detect this reaction, this being the reaction that we're going to look for, one had to prove that this reaction occurred. One had to test each term in the reaction. Well, the neutrinos we could test by putting up so much shielding in front of us between our detector and the reactor that the only neutrinos could come through, and furthermore, they should only be coming through this shield when the reactor is running. So we should get a signal when the reactor is running and only background when the reactor is turned off. That would test the first term. The second term we could test by putting water and getting a signal, hopefully. Water or some organic substance containing protons, and get signals from this, and then replace that water by something else which physically is almost the same but which does not like neutrinos as much as protons do, and that turned out to be heavy water. So we could replace this light water with heavy water, replace the protons with deuterons, and deuterons don't like neutrinos as much as protons, and so the cross-section is about 1/30th that of protons, and so our signal should drop by that amount. The next term is the neutron. The neutron we know captures, as I've indicated, in protons, giving gamma rays, but it takes about 100 microseconds or so in water for that to happen. So we thought of adding something such as cadmium. Cadmium likes to absorb neutrons, but only when they're slow. These neutrons are emitted fast. They have to slow down. And we could add some cadmium as cadmium acetate or cadmium chloride or something to the water and capture these neutrons and then measure the amount of gamma rays that came off. And we should get about 8 MeV of gamma rays that came off. And as the neutron only captures when it's slow, if I draw this diagram of the rate of capture versus time, this is time following the appearance of the neutron, the fast neutron, and this is probability for capture. It would start off at very low probability, rise to a maximum, and then decay away. And one would have a neutron capture curve in time that looked like that. That would give us the delay between the pulse of the positron, which happened very quickly, and the capture of the neutron. Now, by adding less cadmium to the water, if it's a neutron, this curve should look perhaps like that. And by making more cadmium, higher cadmium concentration in the water, the curve would look like that. And we used computer simulations and could calculate quite accurately what this curve should look like. And so we should test then the fact that this is a neutron. Finally, the last term, the positron, is very characteristic. It always emits, almost always, when it captures with an electron, emits 2 gamma rays. And these 2 gamma rays are half MeV, or 0.51 MeV each. Furthermore, these 2 gamma rays go off in opposite directions from the site of this electron capture. So one had to just detect the fact that 2 gamma rays came off at opposite directions from the water and that they were half MeV each. Well, this then was the scheme. Finally, the last factor that came in to the story was the development of liquid scintillators. Crystal scintillators had been discovered some 10, 15 years earlier. Now liquids, certain organic liquids, had been found to scintillate. That is, when a gamma ray or an electron came through the liquid, they would excite. The gamma ray would produce an electron in any event, and the fast electron would excite the molecules of the organic liquid, and the liquid then would de-excite and emit some light. And the development of phototubes, which were so sensitive that they could detect down to 1 and 2 photons of light and detect them with high efficiency. These are called photomultipliers, and your instructor can, if he hasn't already done so, tell you about how a photomultiplier works, but it can amplify the current from 1 photon of light. It can produce a tremendous number of electrons at its output. So it's very sensitive. Well, liquid scintillators at that time had only been made in small quantities, a tablespoonful or so, but we needed large quantities. We needed tons. we wanted the liquid scintillator, in one instance, to supply the protons, or at least to give us so much detection volume that we could surround a large volume of water with this liquid scintillator. Well, our group, we had a very fine group of people at Los Alamos, including some chemists, other physicists and electronics people, and we found how to make liquid scintillator in large volume, and it can be made in arbitrarily large volume, and so one could then build a big detector. We made a first experiment at Hanford, the Hanford Engineering Works, where the country's newest reactors were just going up, out in the state of Washington, and we came back having pushed the cross-section not to 10 to the minus 43 square centimeters, but we had an upper limit on that cross-section of 10 to the minus 39 square centimeters. And we were stopped at that point by the discovery of cosmic rays. Now, you thought cosmic rays were discovered a long time ago by other people. Well, they were. It's just that we discovered them again. We had completely ignored the cosmic rays, hadn't given them any thought. Turned out that the detector could be shielded from the reactor very well, but we hadn't shielded well enough from the cosmic rays. So we came back to Los Alamos in 1952, relayed our plans, rebuilt the detector, made it bigger, and then laid plans to go not to Hanford but to the Savannah River plant of the Atomic Energy Commission, where even larger reactors were just coming up to power, producing a very large flux of neutrinos, and we found that we got permission to get near one of them. And so we built the detector and took it down there and installed it in 1955. And the detector looked something like this. There was a thin layer of water, a few inches thick, in a large can of thin sides, this being water, so there's our protons, perhaps a ton of water. And then next to that water was a large can of liquid scintillator. So this is scintillator, and this is scintillator. And then a few hundred phototubes, photomultipliers on each end of this system. And now we had everything we needed. The water being in here, the neutrinos would come from the antineutrinos would come from the reactor. They would interact. There would be quickly the positron pulse coming from the annihilation of the positron. The neutron would be slowing down and wiggling around in this water as it slows down, and then capturing cadmium, and one would now have a burst of gamma rays coming from that capture and have the two pulses. Just to be doubly sure, we built this twice as big. We added another can of water here and another region of liquid scintillator down here. And so we had two detectors, and we had to require that these detectors would act exactly the same way, that the signals from each of these detectors, this triad, would be the same. Well, from there on, it was just work. It was fun. We worked about a year. We had calculated that the counting rate for this event should be about 3 or 4 counts per day. That's exactly what it turned out to be, within a few uncertainties. So it isn't exactly, it's approximately what it turned out to be. It turned out that it was twice too high from what we had calculated, but that was soon solved by, that problem was solved by the parity, failure of parity, conservation of parity, which again I refer you to your instructors for, which doubled the cross-section. We waited for the reactor to turn down to turn off, and the signal would disappear, and then the reactor would turn on again. They didn't do this for us. They just did this. Everybody there wanted to keep the reactors running as much as possible, but we'd walk around with long faces waiting for them to break down. They'd break down, and we'd be happy, and they'd say that we had put a jinx on them. So we'd get background counts. We replaced the water with heavy water with cadmium in it, and the signal dropped. We changed the amount of cadmium for the neutrons, and that changed the counting rate of neutrons. And finally, we put absorbers in between these sections and could check the fact that the gamma rays were in fact half MeV. Well, this was the observation then of inverse beta decay, catching the thief with the energy in his pocket away from the scene of his crime. Much has happened in the story of neutrinos since then. Not only do we have neutrinos such as I've been talking about, but we have other kinds called muon neutrinos, which again I refer you to your instructor for. And in fact, we're using neutrinos now to penetrate nuclei and nucleons at extremely short distances, and so probe the atomic forces and the constitution of the nucleon and of the proton itself. I thank you for your time, and I'll pause a moment to see if there are any questions. Say goodbye.